guys, today we are going to be talking about why the sign of delta G, so basically when delta G is negative, determines whether a term is spontaneous, especially because in order for a process overall in the aspect to be spontaneous, the delta S of the universe needs to be positive. So why the heck does delta G need to be negative? For one, let's just talk a little bit, like a little brief overview of delta S, the system in the universe. For one, the universe, delta S of the universe, delta S, the S is entropy. Entropy literally meaning chaos or disorder. If you have a negative value for chaos or disorder, that clearly means that entropy is going down, right? So positional entropy is something to talk about, right? I'm going to actually show you an example. So right here, positional entropy. Okay, so when we look at positional entropy, we can look at it as a solid, liquid, or gas state. The entropy of a solid will always be lower than that of a gas, because the idea here is that the gas has more, has a higher ability, higher space, right? It doesn't have a definite volume or shape to move around, to dance around, to do whatever it wants, but a solid has both a definite volume and a definite shape. So this is the idea here. I'm going to go back to here. Okay, so this is like the slight idea behind delta S of the universe and that. And the reason that delta G is going to be negative, obviously, is because that means that delta G has to do something with this, right? So in order for this to be negative, clearly to be positive, clearly these must be like positive and positive, or like one negative but one a larger positive, or something like that, right? Something within the components. So I'm going to explore the components of this reaction today and explain to you why delta G must be negative in order to keep delta S positive. So I actually have like a little writing I did. I was going to just write it as I talked, but I take really long to write, so I copied it. Okay. I'm going to debrief this step by step. For one, free energy, okay? So I'm going to pull this up here. Show you guys. So here's free energy. Free energy gives free energy or free energy. This is our set formula, okay? This is the set formula for free energy. This tells us that the enthalpy minus the temperature times the entropy gives you your free energy. So, with this being said, if we look at this, we are always technically looking sort of for we're looking for an equation. We're looking for something. This delta S right here is representing the system, the delta S, the entropy of the system. It's not going to be representing the surroundings because you're considering it from the system's point of view. It's not physics. We're not considering surroundings right now. We will in a second. Okay, with that being said, let's say I want to isolate this, right? I want to find out how the heck does this plus this make any equivalent. So if I'm looking at this and I divide out the negative temperature, I'm going to actually use a pen. I divide everything here by negative T. I will get that the G over negative T equals the enthalpy over negative T minus the entropy, right? Sorry, I'm divided by negative, so it cancels out. So plus the entropy. And this entropy is my system. But that is also telling me that this right here is actually the entropy of my surroundings. It is, because something plus the entropy of the system equals the whole free energy available. So I just wanted to show you how I get to this equation. Now I'm going to explain it better in depth. Okay, so we're going to move this up here a little bit. So now, with this equation, we're basically saying that this right here is going to equal the entropy of the surroundings, right? The entropy of the surroundings plus the entropy of the system. And what we should remember if we think about this in this equation right here, the entropy of the system plus the entropy of the surroundings is the entropy of the universe. So that means that we can make the connection that solving for the free energy can determine whether the entropy in the universe is positive or negative, meaning whether it is thermodynamically favorable, a reaction is thermodynamically favorable, or whether it is not. So why delta G has to be negative? Well, we've already established that we want delta S to be positive, right? Positive means there is chaos, there is disorder, which means if we have this formula right here, this basically, we can sum this whole thing down to say, I can literally erase all of this and say that since I can say that delta G over my temperature equals the entropy of the universe, right? Because this comes from here, and this we said is going to be your system, and then this by the T is going to be your surroundings. So now, this basically means that delta G over T equals this entropy of our universe. But we said we need it to be positive. We need this to be positive. It does not work if it's negative. It's the universe doesn't like it. It's ugly, basically. So if I have a negative symbol here, and I have a positive here, and I have a positive here, because I cannot, by the way, your temperature can't be negative. You measure on the Kelvin scale. We have not reached, obviously, absolute zero. So if this is negative, if delta G is a negative number, let's say -5, and this is 200, then I have a negative here. These cancel. You get what I'm saying? So now, your delta S of the universe is a positive number. And that's why delta G has to be negative.